Oh, now it's below. Now I can do it. So RS, I'm sorry, VRS. We need to do VRS. We can't do RS yet. I mean, IRS yet. But what we're going to do is we're going to use VRS max, and then we're going to do VRS minimum. And we can do these in any order. So what's this going to equal to? Now let's do the 8, which is our input voltage, minus our Zener voltage, 5.6, and that would give me a maximum voltage of what? 4 volts. Our minimum is going to be 7 minus 5.6, and this gives us a minimum of what? 1.4. Okay. So to calculate the size of RS, or calculated, right? You'll understand that. I need to put this. This is calculated, but this is not the one we're going to use. So your calculator is never going to be the one you use, right? You understand that? It's always going to be lower. Then we're going to use the minimum voltage that it'll ever drop, 1.4, over the maximum current it would, maximum load current, which would be 100 milli plus IZK, which would be 1 milliamp. Minimum voltage over the maximum current, right? Is that rounded up or rounded down? Right on 14, okay. So we know we're not going to use a 14. We're going to come up here, we're going to choose a size. And I should have brought this up first, guys. So we're going to look at our resistor chart, right? Standard resistors. And we're going to look at 5%. And we don't have a 14 ohm, but we got a what? Got a 13. So we'll check our tolerance, make sure someone say, 13 times 1.05, and that gives us what? 13.65. So it looks like it'd be okay to use that, right? So RS we'll use 13 ohm. And then we're going to calculate the wattage. PRS would be equal to your maximum voltage, right? 2.4 squared over 13. So I chose oh wow. I chose the 12, huh? Okay, so what we got? 443 milliwatts. Yeah, very important for us to know the units. So that means we would use a 1 watt resistor, right? I'm not asking y'all to choose the resistors. We're just doing this calculation. So now we need to calculate the power on our resistor. So we can calculate RS max, IRS max. This is going to be when it drops its maximum voltage divided by the size of the resistor that we chose. So I can calculate the power of my Zener. I'll use the voltage, Zener voltage 5.6, and then I'd multiply that times, and the formula is the I of the load. I'm sorry, IRS max, right? Minus I of the load minimum. What's I of the load minimum? 0, right? So we'll just multiply this by 185 milli. And what does that give us? $1.03. So that means we wouldn't use a 1 watt Zener. We'd find another one, right? But we're just doing the math here to understand what's going on. So we'd go and find another Zener. Go to internet and type 2 watt Zener, right? Okay, so okay. As long as it's not over 19, it's okay. Now on number 3, remember the Zener circuit would should look like this, right? Because number 3 is a what? Negative supply, and the Zener goes in there backwards. I don't remember. So they all, work the same, right? Okay, except the only difference is on number 3, the Zener would be in this way right here. But when we do our calculation, we always use what we call absolute values, which means what's an absolute value? The number without the sign, right? So that's all. The only thing different. Your math is going to use absolute values, but the way you hook up your circuit, because we don't have minus currents, right? And we don't have minus watts, and we don't. So guys, if y'all can get this one, y'all should do okay on the circuit that's going to be on the test. So let's hook this up. Let's go to Electronic Workbench and hook this up. We're using a what? 1N4734. Now the only thing that I don't specify, remember, the one in 3734 has a tolerance. And what's the tolerance? Y'all remember? So here, what y'all should have probably said is the one in 4734A. Yeah, so the A is a 5%, and if you don't put it, it's what? It's a 10%, right? You understand? Sometimes it's not critical. So I think all the ones that we have are A's, I think. So the Zener lab, this is what you're going to do on the Zener lab. Is you're going to calculate what Zener, you're going to pick a Zener, you're going to wire the circuit up, and you're going to come up here and you're going to vary. Now, the only way we can vary the current is to use a rheostat, right, or a pot wired as a rheostat. So when you look at the lab, we're going to choose a size for RS, and then we're going to choose a Zener, and we're going to, it's a positive supply. I can't remember what it is over here. And then we're going to come up here, and just to keep from burning up our pot, we're going to use a 100 ohm resistor, and then we're going to put a potentiometer wired to act like a rheostat. And we're going to measure load current. Now, what's nice about using a 100 ohm resistor is that we can measure the voltage across. We can use the 100 ohm resistor as a shunt, right? You understand that? Which means we can measure the voltage across the 100 ohm and calculate the what? The current. So it's going to be, so if I measure 3 volts and I divide that by 100, what's that going to be? So I is equal to V over R, right? So what would that be? What's that? Okay, so right now you know that every volt is going to be 10 milliamps. So you don't have to do calculations anymore, right? And what you're going to do is you're going to measure the voltage across here, across the entire load, right? Does that make sense? To see what percentage your regulation is. So you know it's not going to the Zener is not going to regulate perfect, right? You understand that? So what we're going to do is we're going to go from full load to no load. We'll get our output voltage. So your Zener is going to have a Zener voltage, and we have what we call percent regulation. So your Zener voltage is what you want, right? You understand that? And then we'll come over here and we'll just subtract. Let's see, how does that go? V out minus DZ. But actually, it's actually big over little. It's big minus little. So you would swap this around depending on which one is the highest, right? Does that make sense? Yes or no? So this is the way we calculate percent error. Is we take what we want, right? You understand? And then we subtract that from what we got, or vice versa, depending on which one's bigger. And then we multiply that by 100, and that gives us what we call percent regulation. And this is basically what we do when we give you a grade on a test, almost exactly. So I take what's possible, I subtract how many you missed, right? You understand that, and I divide it by what's possible. So, and then I give you a percent error or percent accuracy, right? You understand? So this is the basic formula. But you swap this, it's always what? Big minus little. So VZ might be on the left and V out might be on the right, because we don't want a negative number here, because each one of them would give what we call our percent regulation. And every power supply has a percent regulation. So most of the time when you look at the data, the true data sheet on a power supply, that's one thing that they tell you is actually percent regulation, right? Understand? And this would be when we're under full load and when we're under minimum load, right? You understand that? And then minimum and maximum voltages. Does that make sense? So this is the circuit that we'll hook up. And why we're using a 100 ohm resistor? Well, we're using the 100 ohm resistor. So if you come up here and accidentally turn that pot all the way to 0, you don't have a short, right? You understand that? And then plus there's another feature is that we can use that as a shunt, right? We can measure the voltage across it and use that to calculate current without doing what? Without breaking the current and using an ammeter. Miss Bush is teaching intro to electronics, and she had 4 meters where the students blew fuses. And this is what they do when they get into Ohm's law. They do what? They measure current and they measure voltage. And what do? And they're single resistor circuits. So they'll come over here and they'll have a DC power supply, excuse me. And then we have one resistor. And what they'll do is they'll come over here and they'll come over here and put their meter on volts and measure volts. Then they'll come over here and break the circuit and measure amps. And then they hook up another circuit and their meter's still on what? Amps. And they put it across that resistor, and what does it do? Blows the fuse. So this is what's nice about this. You don't have to worry everything you do. So if you got a series resistor, so if I wanted to measure the load current or the Zener current, how could I measure the Zener current? Well, what we would do is we'd measure the voltage drop across RS, right? And then I could say IRS would be equal to VRS over RS. And then I could subtract what? I could subtract my load current. And then that would give you your Zener current. So one important aspect that people have problems with is figuring out what happens to, so what's the Zener current constantly doing? Is it always the same? It's constantly varying depending on what's going on with the load and what's going on with the input voltage, right? You understand? So as you're in, now one of them's going to be constant. So if the load current is constant and the input voltage goes up, what happens to Zener current? Okay. So Zener current, IZ is always equal to IRS minus I the load. Right, you understand. So if your input voltage goes up, then what's RS got to do? Is it going to drop more voltage or is it going to drop less voltage? Yeah, it's got to go up because I've always got here, if this was regulated, I would always have 2.4 volts across my load, right? You understand. So if my input voltage goes up, then VRS has got to do what? Go up. I, the circuit, is equal to what? This is I, the circuit right here. I, the circuit, is equal to VRS over RS. So if my input voltage goes up and my load current don't change, then Zener current's got to do what? It's got to go up. If my input voltage goes down and my load current doesn't change, then Zener current's got to do what? Zener current's got to do what? Got to go down, right? You understand? So Zener current moves in the same direction as your input voltage if my load current is held constant. And that's the way Ohm's law, when we talk about proportional. So what happens if load current goes up and my input voltage don't change? Well, if the load current goes up, then this guy here is going to drop the same voltage. If this goes up, this conducts the same current. What does my Zener current got to do automatically? Is it going to go down or go up? Huh? So what does Zener current do relative to load current? That's what we're trying to figure out. It's inverse. So if load current goes down, Zener current's got to do what? Got to go up, and if load current goes up, Zener current's got to do what? Got to go down. So it moves in the opposite direction. Now what's happening is that this is all going all over the place, right? You understand? So my inputs varying, my load currents are varying, but that's the way they do. And we got to understand how these things have a relationship to it. Yeah, because it's a Zener diode, but yeah, if you reverse bias it, it would still do the same, right? You understand that? It's well, that's not exactly true. If it was in a circuit that had resistors in it, so what we're trying to understand is what's going on here and what's going on here. Does that make sense? So a Zener diode is normally, if you put a Zener diode in a circuit forward bias, what does it act like? And if you operate it below its breakover voltage, what does it act like? Huh? It acts like a diode. It acts like a rectifier diode, as long as it's operating below its potential. And we do that sometimes. We use it for clipping circuits, where we got some safety margin in there where we don't want the load to ever, if the load ever sees over a certain voltage, it'll burn it up. So what we'll do is we'll put a Zener in there and we operate it. So let's say this guy right here, it's rated at 5 volts and it'll burn up if it ever sees anything over 7 volts. Well, I'd use a 7-volt Zener right there. And what would happen? Well, if it tried to get up above 7 volts, what would the Zener do? It'd just clip it off. Right? You understand that? It'd just clip it off. So we use them for all types of things. We use them back to back, where we come over here in an AC circuit and we wanted to do the same thing. They'll put a Zener, they'll put back to back Zeners. They'll just connect them together like this. And this protects an AC load, right? You understand? So if it ever exceeds the Zener voltage, it'll clip off. It'll clip off the top of the alternation, or it'll clip off the bottom of the alternation. So we use Zeners in all types of that. So what would happen if this went too positive? This guy would act like a diode. This guy would, because it would be forward biased, right? You understand? And it would clip off the positive alternation. So here is one situation where we're using one just like a forward biased diode, and the other one would, and then of course on the negative, which one's protected? This guy's protected on the negative, right? You understand? This guy would be acting just like a diode because it would be forward biased. So you see Zeners used in other applications besides for a lot of clipping circuits. We'll see Zeners in clipping circuits. That's designed to just do what? Just to clip it off. Or in what we call crowbar circuits. A lot of times they'll deliberately blow a fuse in a power supply. To prevent from what? From burning up your load. And so we'll have these, they call them clipping circuits, where if the Zener voltage is exceeded, it blows a fuse. But we got to add another component to that. They're also used in crowbar circuits, where if the output tries to go up above a certain limit, it just cuts it off. So crowbar circuits are different. So we use Zeners all over the place, besides for just what? Power supplies. Anytime we want to limit a voltage to a certain thing, then we'll do it that way. So Zener current varies what? In the opposite direction of my load current, in the same direction as my what? My input unregulated voltage. So that Zener current Zener is automatically varying its internal resistance without you touching it. And so this guy right here is definitely a dynamic device. Resistors, capacitors, and inductors, we call those passive devices. When we get into semiconductors, we start getting into what we call active devices. So any other questions on the worksheet? The last one? Uh-huh. No, on Zeners we never round up. Zeners we never round up, because if I round up, I'm moving toward the knee, right? You understand what we're saying? So what we're trying to do is we're always trying to do what we on Zeners. It's kind of different in that what we're trying to do on a Zener, we're operating over here. So this is Zener current right here, and this is Zener voltage. What we want to do is we want to move in that direction right there. Yeah, which means this is IZ. So I always want to go this way. I don't want to ever. So if I round up, then I'm going. My IZ would be go down, and I'm moving toward the knee. So that means if I calculated 19.9, I would automatically choose a what? I'd round down to 18, and then I would calculate my resistor from there. Does that make sense? Yeah. So this is kind of different. We don't round up on Zeners. We always round what? Down. Yeah, we always round down. We don't ever round up on Zeners. We don't ever round up. We always want to move away from the knee, right? We want IZ to go up. We don't want IZ to go down when we're choosing that resistor, because if we go down, we're moving toward the what? Toward the knee, right? Does that make sense? No. So 19.6 would put it right here. So basically, if you round it that way, you're going to be moving up into the knee, right? That makes sense. So that's why we round down. So we round our calculated down, right? Does that make sense? And then we go to the next lower value when we choose our resistor, and then we check the tolerance. If the tolerance comes up greater than what we calculated, then what we would do is we would go to a next lower value, right? Are we okay? Any more questions? So this lab, the Zener lab is not in the book. There's no Zener lab in your lab. So this is going to be a handout lab. There's one handout lab we need to do too. I keep forgetting. I need to find my parts. We got a handout lab where you check diodes to see if they're good or bad. So what we're going to do is we're going to come up here. So it's basically the same thing. You're going to do what? Give you the specifications for the Zener, and then we're going to calculate the what? Size of RS, right? Then from the list of standard resistors, you're going to choose a size for RF. Then we're going to calculate the minimum and maximum voltage drops across RF. Then we're going to come up here and we're going to put the size of the resistor we're going to use. We're going to put the tolerance and the wattage. Then it says we're going to calculate the minimum maximum power rating of the Zener diode with the chosen RS. Once calculation made, select the proper Zener from your data sheet. And you're going to write the part number down. And then you're going to ask Rich for the part, right? Then you're going to draw the entire design circuit. And I didn't erase mine. So what should your circuit look like? So here, what we're going to do is we're going to simulate a varying input voltage. Oops, what am I doing? So y'all don't know, do you? I think we're going to use a 10. I think we use a 10K pot because that's what we have. And ours are 1 watt. And this is going to be 100 ohms. This is going to be RF. Our Zener, it's a positive supply, so it's going to be place watt, like this. And what we're going to use for unregulated is, well, we're going to use a variable DC power supply. So we're going to simulate unrated. So now we can set our minimum voltage and our maximum voltage, right? That makes sense. So this will be the basic circuit that you're going to hook up. Construct the circuit in the connected circuit. So this is going to be your basic circuit. Construct the circuit in the preceding steps. Connect the circuit using the trainer's positive power supplies as an input. Connect to output. Designed to a 1K ohm resistor wired as a rheostat in series with a 100 ohm quarter watt. Then you'll draw the complete schematic here. That makes sense? Okay. And then I'll check your work. And you'll come up here and you'll set the rheostat for mid-range. Adjust the trainer's power supply to set the input voltage. And you're going to change the input voltage, right? You understand that? And V out when Vin is minimum, V out when Vin is maximum. Then we're going to change our load currents, and then we're going to calculate our, according to the reading recorded in the procedure steps, V out is highest when Vin is, V out is lowest when Vin is, and I is. That makes sense? Yes or no? So you're going to say V out is highest when Vn is something and I the load is. So here it's going to be minimum, maximum, maximum, minimum. And we're going to come up here, we're going to see what's going on, right? And then using the measured values, calculate the percent regulation. Y'all understand how to do that now? Right? Big over little. Right? Huh? Big minus little. So what we're doing is we're saying VZ divided by VZ minus V out, or V out minus VZ, right? You understand? That'll give us our percent regulation. And then you'll write a conclusion on what was accomplished during this lab. So this is the handout lab. So y'all got any questions on that? Okay. So you should have the resistor. If you don't have the resistor in the kits, then you need to ask me, and then you'll have to ask me for the Zener once you get a part number. You'll say I need a 1N And we're going to use the 4700 series. That's what we got. Everybody okay? All right, guys. So we okay on the worksheet? All right, let's go to lab.